Hey everyone, welcome. As your ECE professor, I am absolutely thrilled to be guiding you through this explainer today. Our goal is to really nail down the fundamental concepts of communication systems, specifically getting you completely prepped and ready for your ECE and diploma exams. So, let's jump right in. Think about something we do literally every single day. Have you ever wondered about the incredible journey a simple voice message, just a quick hello, takes to reach someone thousands of miles away, almost instantly, without getting lost or scrambled? It feels kind of magical when you stop to think about it, but it's all grounded in really solid, testable engineering. Here is our agenda for today's explainer. Welcome to Communication Systems, the basic block diagram, understanding noise and channels, what is modulation, why we need modulation, and finally, an ECET exam quick revision. All right, Section 1, the basic block diagram, the signal's journey. This 5-step flow is a classic guaranteed exam question. It maps out the exact path every single piece of electronic information takes from its starting point all the way to the finish line. Let's break it down step by step. So, starting right at the beginning, we've got the information source. This is exactly what it sounds like. It's the origin of the data. In the real world, this could be you talking into a microphone or maybe typing an email on your keyboard. It's just the raw data waiting to hit the road. Next up, that raw data hits the transmitter. Now think of the transmitter like a master translator. Your voice can't just magically fly across the country on its own, right? The transmitter processes and converts it into an electrical signal that's actually built to travel those long distances. I'm going to skip over the middle block just for a second and jump over to the far end, the receiver. The receiver's whole job is to catch that translated traveling signal and pull the original message back out. It basically just reverses whatever the transmitter did so we can understand the message again. And that brings us to the destination, the end of the line, the final recipient. That's just the person on the other end of the phone call listening, or a loudspeaker blasting sound out into a room. Moving right along to Section 2, understanding noise and channels, the middle pass. Okay, so let's look at that middle piece we just skipped. What actually connects the transmitter to the receiver? That is your communication channel. Think of it as the highway your signal drives down to get from point A to point B. This medium could be a physical copper wire, fiber optic cables, or just straight-up free space if we're using wireless antennas. But, as you probably guessed, this highway isn't perfectly paved. Out there in the channel, our signal runs into the ultimate villain for any ECE engineer, noise. Now, for your exams, you need a rock-solid definition for this. Noise is defined as unwanted, random electrical signals that interfere and distort your transmitted message in the channel. It's exactly like trying to have a deep conversation in a super crowded, loud restaurant. All that background chatter just ruins the communication quality. Electrical noise does the exact same thing to our signals out there. Which brings us to Section 3, what is modulation? The hero of ECE. So how do we beat that noise and travel huge distances? Modulation. Officially, it's the process of varying a characteristic of a high-frequency carrier wave in accordance with our low-frequency information signal. Let's make that super simple. Imagine trying to throw a flat piece of paper across a field. Doesn't go far, right? But wrap that paper around a heavy rock, throw it, and boom! It flies a massive distance. The paper is your message, the rock is the carrier wave, and the act of wrapping it, well, that's modulation. For your diploma exams, you absolutely have to lock these 3 main types of modulation into your brain. Amplitude modulation, or AM, frequency modulation, FM, and phase modulation, PM. Depending on whether you tweak the amplitude, frequency, or phase of our carrier rock, you get a different type of modulation. Next up, Section 4, why we need modulation, 5 essential reasons. This is a heavily tested topic. Why go through all the trouble of modulating? There are 5 core reasons you need to know. Reduction of antenna height, multiplexing, increase in communication range, avoiding mixing of signals, and reduction of noise. Let's break a couple of these down practically so they really stick with you. Take the reduction of antenna height, for example. Get this. The physical height of an antenna has to be proportional to the wavelength of the signal it sends. If you tried to transmit low-frequency human voice without modulation, your cell phone antenna would literally need to be thousands of meters tall. We're talking up to 10,000 meters. No way that fits in your pocket. Modulation increases the frequency, shrinks the wavelength, and keeps our antennas wondrously small. Then there's multiplexing. Think of multiplexing like organized carpooling on our channel highway. It safely lets multiple signals share the same medium efficiently. Without modulation, if everyone just blasted their raw baseband voice signals at once, we'd get a disastrous mixing of signals, total chaos, massive interference, and you wouldn't understand a single word anyone was saying. Bottom line here, unmodulated signals are just weak. They have a really short range and they get absolutely crushed by noise. But the second we modulate them onto a high-frequency carrier, total game changer. We massively increase our communication range and practically armor our signal against that annoying noise we talked about earlier. Finally, Section 5, ECET Exam Quick Revision, Exam Prep. Okay, let's wrap this explainer up into a neat little checklist for your exam prep. Before you walk into test day, make sure you can sketch out that 5-step block diagram from source to destination. Be able to confidently define the channel and noise. Memorize the exact definition of modulation along with AM, FM, and PM. And lastly, have those 5 needs for modulation ready to go. You do that and you are absolutely going to crush this section of the exam. I want to leave you with a quick provocative thought before we go. If wrapping our signal around a carrier wave lets us shrink antennas and shoot messages across the globe, how on earth are engineers pushing this exact same tech to talk to satellites floating in deep space? Keep that engineering curiosity fired up as you study, and we will explore that fascinating topic in our— It's going to take some pretty dry telecommunications theory and turn it into an epic real-world journey of a signal. I am absolutely pumped to guide you through this today. We're taking those classic textbook concepts of communication systems and turning them into a visual masterclass. It is perfectly tailored to prep you for your ECET exams, and by the end of this, we're going to lock down exactly how information travels from point A to point B. Here is the roadmap for today's masterclass. We've got 1. Signals and modulation basics. 2. Types of wave modulation. 3. Bandwidth and Hartley's law. 4. Internal and external noise. 5. AM equations explained. And finally, 6. An ECET revision summary. Section 1. Signals and modulation basics. The passengers and the train. Let's get right into it. So before we get bogged down in any complex math, you gotta ask yourself a fundamental question. How on earth does a human voice cross an entire ocean? Think about that for a second. We obviously can't just shout loud enough, right? Our voices, or really any standard data we generate, operate at low frequencies. They literally just don't have the energy to travel vast distances through the air or through cables without totally degrading. They absolutely require a high-speed, high-energy vehicle to carry them across those massive spaces. And that brings us to our very first crucial definition, the baseband signal. Think of the baseband signal as our passenger waiting on the platform at the train station. This is your original message. It's your actual voice, your text message, your video data, the raw information that needs to be transmitted before anything has been done to it. It holds all the important information, sure, but it doesn't have the legs to make that long journey on its own. So, what builds our transmission system? Enter the carrier signal. If the baseband signal is our waiting passenger, the carrier signal is the high-speed train itself. It's a powerful, high-frequency wave. But here's the catch. It is unmodulated. And by unmodulated, I mean it's perfectly uniform and carries absolutely zero information on its own. Literally none. Its sole purpose in life is just to cover long distances quickly and reliably. Now, when our passenger finally boards that train, the result is the modulated signal. This boarding process, putting the message onto the carrier, is called modulation. It's the technique of successfully combining our low-frequency message signal with our high-frequency carrier wave for transmission. You guys, understanding this trio, baseband, carrier, and modulated signal, is an absolute must-know for your exams. Section 2, Types of Wave Modulation, How the Passenger Rides. Okay, so the train is ready and the passenger is on board. But there are actually a few different ways that they can ride this carrier wave. Let's look at the modulation hierarchy. The classification basically splits into 2 main families. First, we've got pulse modulation, which is used for those digital-style bursts. This includes pulse analog modulation, your PAM, PPM, and PWM, along with pulse digital modulation, primarily PCM. But our main focus for today is the other family, continuous wave modulation. This branch splits neatly into amplitude modulation and angle modulation. And angle modulation itself, well, that breaks down further into frequency modulation and phase modulation. This breakdown brilliantly illustrates exactly how those continuous waves work. In amplitude modulation, or AM, the amplitude of the carrier wave is what changes according to the message signal. Visually, the wave grows taller and shorter based on your voice, while its frequency and phase stay exactly the same. In frequency modulation, FM, the frequency changes according to the message, so the waves squeeze together and spread apart, while amplitude and phase are completely frozen. And in phase modulation, PM, the phase of the carrier shifts, meaning it changes its starting position while amplitude and frequency are locked in place. Now listen up, because this is a massive ECE exam alert. The most crucial point to remember here: always remember the constants. Professors absolutely love testing you on what does not change. Students always remember what varies, but you've got to remember the constants. If it's AM, frequency and phase must remain constant. No exceptions. Lock that rule into your brain right now.
Section 3, Bandwidth and Hartley's Law, the highway and speed limits.
So once our modulated signal is fully built and ready to rock, it needs a physical highway to travel on. This brings us to bandwidth, and we need to distinguish between two types here. The baseband bandwidth is just the size of our original message. It's the range of frequencies present before any modulation happens. But the channel bandwidth, that is the width of the physical highway required in the transmission medium to actually send that information efficiently. Think of it like this. A higher channel bandwidth allows more information to be transmitted, exactly like a wider highway lets more cars pass through at once. And the rule governing that highway is Hartley's Law. Hartley's Law sets the ultimate traffic rules for communication. It states, mathematically, that the total amount of information you can transmit is directly proportional to the channel bandwidth multiplied by the transmission time. It's that simple. If you want to send more data, you either need a wider channel bandwidth or you just have to wait longer and increase your transmission time.
Section 4, Internal and External Noise, the hazards of the journey. Now, as you might guess, the transmission journey is rarely perfectly safe. As our signal cruises down this bandwidth highway, it has to battle these villains known collectively as noise. And noise classifies into two major camps. First up is internal noise. This originates inside our own equipment. Think thermal noise from resistors. The key takeaway here is that internal noise is highly predictable, and because it's predictable, it can be significantly reduced by good engineering and solid circuit design. On the flip side, we have external noise. This originates outside our system. We're talking atmospheric static from a lightning storm or industrial noise from heavy machinery nearby. It is completely unpredictable, which makes it extremely difficult and sometimes totally impossible to eliminate. Basically, internal noise is like the hum of a cheap car engine that we can fix. External noise is the sudden thunderstorm we just have to survive. Section 5, AM equations explained, the mathematical blueprint.
All right, let's dive into a bit of math. We've talked concepts, so let's pull back the curtain and look at the actual time domain mathematical blueprint of our amplitude modulated wave. And hey, don't let the math intimidate you. It tells a really logical story. We build this waveform piece by piece. Step 1 is our carrier expression. That is our high-frequency baseline sine wave. Step 2 is our message expression, our low-frequency data, the actual voice or text. Then, step 3 is the combined time domain expression. This is where we mathematically combine them. We essentially multiply the carrier wave by a factor containing our message signal, using a special coefficient to dictate exactly how much the message shapes the carrier's amplitude envelope. And that special coefficient brings us to our next key term, which perfectly illustrates the core of AM math, the modulation index. By definition, it's the mathematical ratio of the message signal's amplitude to the carrier signal's amplitude. Now, for your exams, you don't just need to memorize the formula, you need to grasp its physical meaning. This index represents exactly how much our high-speed train is being modified by the passenger inside it. If the index is too high, the wave distorts. If it's too low, the signal is weak. It is literally the ultimate balancing act of amplitude modulation. Section 6, ECET Revision Summary, the Masterclass Cheat Sheet. We have covered a massive amount of ground today, from the station to the final destination. Let's do a rapid-fire revision of the absolute most critical concepts you need to ace this topic on your exams. Lock these in right now. Number 1, your signal definitions. Baseband is your passenger, carrier is your high-speed train. Number 2, the constants. In AM, amplitude varies while the rest stay constant. FM, frequency varies. PM, phase varies. Number 3, Hartley's traffic rules. Information equals bandwidth times time. Number 4, the hazards. Internal noise is predictable and fixable. External noise is unpredictable and atmospheric. And finally, number 5, the modulation index is simply the message amplitude divided by the carrier amplitude. So, the crucial point to take away today isn't just a list of formulas to memorize. As you're studying these concepts, I want you to look at your phone or your computer screen right now and ask yourself, how many millions of modulated waves and bandwidth highways is it navigating this very second? How on earth is it battling external noise right now just to deliver my voice to your ears? The theory you're learning today is the exact invisible magic powering the modern world. Keep that curiosity alive. And welcome to this explainer on analog communications. Today, we are setting the stage for a really energetic, step-by-step masterclass that is absolutely perfect for your ECT preparation. We're going to take the complex math of amplitude modulation and break it down so logically that, honestly, you'll be solving these problems in your sleep. If you want to understand exactly how we evolved from basic AM all the way to the highly efficient SSB-SC systems, well, you are in exactly the right place. Let's get started. Here is our game plan for today. We'll start with 1, modulation index basics, then 2, AM spectrum and power, followed by 3, the power waste problem. After that, we'll look at 4, saving power with DSB-SC, 5, maximum efficiency, SSB-SC, and we'll wrap up with 6, an ECET final formula revision. All right, let's jump right into section 1, modulation index basics. So to really wrap your head around modulation, I want you to imagine you're packing a delivery truck. The high-frequency carrier wave, that's your truck. And your low-frequency message signal, like your voice or your data, that's the cargo. The modulation index, which we denote with a little m, measures exactly how full our delivery truck is. Mathematically, it's just a simple ratio. The maximum amplitude of the message signal, AM, divided by the maximum amplitude of the carrier, AC. So M equals AM over AC. Pretty straightforward, right? And just a heads up, your textbooks might call this the modulation factor or even depth of modulation. Don't worry, it's all the exact same thing. Now, the value of M usually sits somewhere between 0 and 1, and it completely dictates whether our signal survives or gets ruined. We have 3 crucial states you absolutely must mark down for your exam. First step is undermodulation, where M is less than 1. The truck isn't totally full, but hey, the cargo is safe. Second, we have critical modulation, where M is exactly 1. This means it's 100% perfectly packed. But the third one, overmodulation, where M is greater than 1. This is where you've packed way too much cargo. The doors literally burst open and the message gets completely distorted. In a real-world circuit, if this happens, we just cannot recover the original message cleanly. Let's do a really quick micro recap before we analyze the heavy math. The biggest takeaway here is that the modulation index M simply tells us how perfectly our message fits onto the carrier wave. Keeping M less than or equal to 1 ensures our signal stays clean, crisp, and undistorted. Are we clear on that so far? Excellent. Let's move over to the frequency domain. Moving right along to section 2, AM spectrum and power. Okay, so we know the theory, but what does this actually look like when we break it down into frequency components? An AM frequency spectrum gives us 3 distinct parts. Right in the middle, standing tall, is our carrier frequency, FC. But the real magic happens on the sides. We generate a lower sideband sitting at FC minus FM and an upper sideband at FC plus FM. Remember, FM is just your modulating message frequency. So try to visualize this. A big carrier spike in the center, flanked symmetrically by 2 smaller sidebands. And keep in mind, the carrier amplitude is AC, while the amplitude of each sideband is AC times M divided by 2. Now listen carefully here, because this right here is a golden exam equation. We absolutely need to understand the relationship between total power, PT, and carrier power, PC. The formula is PT equals PC multiplied by the quantity 1 plus M squared over 2. Guys, this is the backbone of almost every single AM numerical problem you'll see in the ECET. If you have the carrier power and the modulation index, boom, you can instantly find total power. The carrier power itself, PC, is simply AC squared divided by 2R, where R is the antenna resistance. Make sure you lock this in your memory. Which brings us to a huge realization in section 3, the power waste problem. Here is where we really need to put on our engineering hats. Standard amplitude modulation looks great on paper, sure, but let's check the actual power distribution. Let's assume critical modulation, where M equals 1. If we plug this into the equation we just learned, we find out something pretty terrible. A massive 66.66%, literally 2/3 of our total transmitted power, is consumed entirely by the carrier wave. Meanwhile, the lower sideband gets 16.66%, and the upper sideband gets the other 16.66%. So 2/3 of our hard-earned energy just goes into the carrier. And this brilliantly illustrates the biggest problem in traditional analog communications. I want to pose this critical engineering question directly to you. Think about it. The carrier is just a high-frequency sine wave, right? It contains absolutely zero actual information from our message. All the actual data, your voice, the music, is sitting in those sidebands. So if the carrier carries literally no information, why on earth are we spending 2/3 of our power budget to transmit it?
So quick recap for you. Standard AM is highly inefficient. We just proved mathematically that 66.66% of power is totally wasted on an empty carrier. When M equals 1, the sidebands hold all the actual data, while the carrier just drains our energy. As engineers, we simply cannot accept this kind of waste. We have to fix it.
Let's fix that in Section 4, Saving Power with DSP-SC. This brings us to a brilliant, elegant solution: suppressed carrier techniques. Let's look at double sideband suppressed carrier, or DSP-SC. The logic here is beautifully simple if we take it step by step. Step 1. Well, if the carrier wastes power and carries zero information, let's just suppress it. Delete it entirely from the transmission. Step 2. Transmit only the upper sideband and the lower sideband. And step 3. By doing this, we immediately save massive amounts of power. The total power equation literally just drops the carrier term, leaving us with only the math for the two useful sidebands. So what is our exact percentage of power saving? For unity modulation, where M equals 1, the exact percentage of power saved with DSP-SC is 66.66%. You absolutely need to have this vital stat memorized for the ECET. By simply stopping the transmission of that empty carrier, we instantly save 2/3 of our transmitter power. In the real world, that means smaller power supplies, way less heat, and much cheaper transmitters. Now, what about the bandwidth? Even though we suppressed the carrier right in the middle, the overall frequency range hasn't actually shrunk. The spectrum still stretches all the way from the bottom of the lower sideband to the very top of the upper sideband. Therefore, the DSP-SC bandwidth is exactly the same as ordinary AM. It is 2 multiplied by FM, where FM is your maximum modulating frequency. Now for the ultimate evolution in Section 5, maximum efficiency with SSB-SC. Okay, we saved 66.66% of our power, which is awesome. But, as engineers, we always ask the next question: can we optimize this even further? Think about the two sidebands we are still transmitting in DSP-SC. What's really fascinating is that, mathematically speaking, these sidebands are perfect mirror images of each other. They contain the exact same information. If your receiver picks up the USB, you have the whole message. If it picks up the LSB, you still have the whole message. So, transmitting both of them together, it's completely redundant. We are still wasting precious energy and bandwidth. So, we introduce single sideband suppressed carrier, or SSB-SC. Here are the immense benefits. First, we suppress not just the carrier, but also one of those mirror image sidebands. You can drop the USB or the LSB, honestly, it doesn't matter. Second, we transmit only half the original AM signal. This maximizes our power efficiency to the absolute theoretical limit, because every single watt of power is now going directly into transmitting useful non-redundant information. And as a huge bonus, because we dropped a sideband, we just cut our required bandwidth exactly in half. Let's just lock in this evolutionary timeline before we hit our final formulas. Standard AM, waste power. DSP-SC solves the biggest problem by dropping the carrier. And then SSB-SC takes it to absolute perfection by dropping the carrier and one duplicate sideband. It is just a beautiful, logical progression of engineering problem solving. Finally, Section 6, your ECET final formula revision. All right, students, time for the high-yield summary. Honestly, take a screenshot right now because these are your essential tools for exam prep. First, the modulation index, our trick packing ratio. M equals AM by AC. Remember to keep it at or below 1. Second, total AM power. Peach equals PC times the quantity 1 plus M squared over 2. Always remember that if M equals 1, 2/3 of this total power is just sitting in the carrier. Finally, DSP-SC bandwidth is 2 times FM. But for SSB-SC, please remember that the bandwidth is just FM since we literally cut it in half. Practice your numericals with these and you are going to score full marks for sure. We'll wrap up today's masterclass with a somewhat provocative thought. We just proved mathematically that SSB-SC is perfectly efficient, right? It saves maximum power and halves the bandwidth. So, here is my question to you. Since SSB-SC is so flawlessly efficient on paper,
What physical hardware limitations in real-world transmitters and receivers might prevent us from using it for absolutely everything? Think about the sheer complexity of filtering out a sideband that
Welcome back,
cleanly in the real
class.
world.
Today, we're diving right into a brand new explainer on communication systems. We're going to break down exactly how we manipulate radio waves to transmit information efficiently. I am absolutely thrilled to guide you through this material because understanding these core fundamentals is literally the bedrock of modern telecommunications.
Have you ever wondered how we actually pack high-quality audio into a radio wave without losing the signal? It's a fascinating problem, isn't it? Today we're going to explore the evolution of how engineers solved this, moving from really simple amplitude tweaks all the way to advanced frequency manipulation. We'll look at exactly why early radio sounded so incredibly scratchy and how mathematical breakthroughs allowed us to transmit crystal clear audio across vast distances.
Here's our syllabus for today's lesson. First, understanding SSB and VSB. Second, what is angle modulation? Third, the math behind FM. Fourth, deviation and modulation index. And finally, comparing AM, FM, and PM. Let's get right into it.
Section 1. Understanding SSB and VSB. Let's look at how we upgraded early amplitude modulation to make it much more efficient.
So, you know basic AM radio, right? Well, it takes up a ton of space and power. Enter single sideband, or SSB. Now, SSB is brilliant because it literally halves the bandwidth of standard AM, it saves a significant amount of transmission power, and it drastically reduces both fading and noise. But there's always a catch, right? The trade-off is highly complex transmitter and receiver designs. And because of this sheer complexity, SSB is mainly used for basic speech signals. It's really pretty much unsuitable for high-quality music transmission.
That brings us to vestigial sideband, or VSB, which acts as the perfect middle ground. Think of it as the Goldilocks solution. It uses a bit more bandwidth than SSB, but less than standard double sideband. It gives us better power transmission, and most importantly, it provides crucial protection against phase distortion since there's no loss of frequency components. It's just a clever compromise engineers use when they need a little more quality without wasting too much space.
Moving on to Section 2. What is angle modulation? We are completely shifting gears here.
Notice the fundamental shift here, class. With amplitude modulation, the height of the wave was constantly fluctuating. But in angle modulation, the carrier amplitude is locked firmly in place. It remains totally constant. Instead, we're now manipulating the phase angle of the wave based on the message signal's instantaneous amplitude. This one single shift is exactly what unlocks high-fidelity audio.
Under the umbrella of angle modulation, we basically have two specific types. First up is frequency modulation, or FM. So instead of changing the height of the wave, FM specifically alters the frequency, meaning how close together or far apart the waves are, to perfectly mirror the instantaneous amplitude of our message signal.
The second type is phase modulation. PM targets the phase of the carrier wave itself, changing it according to the message signal's amplitude. But the really important thing to remember is that both FM and PM are united by that constant carrier amplitude we just talked about. And this brilliantly illustrates why FM and PM are so much more resistant to static. You see, static mostly affects a wave's amplitude, which these two methods completely ignore.
All right, Section 3. The math behind FM. Grab your notebooks, because understanding these formulas is the key to mastering this whole topic.
This right here is the time domain expression of FM, which represents the instantaneous frequency of the wave at any given exact moment in time. And hey, don't let the trigonometry intimidate you. It's honestly just a mathematical way of mapping exactly how the wave stretches and compresses.
Let's pull those variables apart so you can see exactly what they represent physically in the circuit. F is our target, the instantaneous frequency. FC is our baseline carrier frequency. Then we have KF, the frequency sensitivity constant, which basically dictates how aggressively the system responds. Finally, VM is the peak amplitude of our message signal. Do you see how the frequency sensitivity constant directly interacts with the peak amplitude of our message to create the final wave? It's pretty elegant. Building on that, the actual FM signal equation gives us the total voltage of the FM wave. Notice a brand new variable nestled right inside the sine function, MF. This little variable dictates the entire behavior of the wave, which is going to bring us straight to our next core concept. Section 4. Deviation and modulation index. This is how engineers keep signals within legal boundaries. First up is frequency deviation, represented by delta F. This measures the absolute limit of how far our modulating signal pushes the carrier frequency away from its center point. It's actually super simple to calculate. You just multiply that frequency sensitivity constant we learned about, KF, by the peak amplitude of the message, VM.
Let's calculate the total swing together using a real-world example. Say we start at a base carrier frequency of 50 MHz, and our maximum deviation is plus or minus 200 kHz. That means our highest frequency hits 50.2 MHz and our lowest drops to 49.8 MHz. So our wave sweeps back and forth over a total span, or swing, of 400 kHz. Now, circling back to that mystery variable MF, or simply M, the modulation index of FM. To find our modulation index, we just take that frequency deviation we calculated, delta F, and divide it by the modulating frequency, FM. It's a really simple ratio, but it tells us exactly how heavily the carrier is being modulated.
Just to cement this concept, if a system has a 25 kHz frequency deviation and we divide it by a 10 kHz modulating frequency, boom, it gives us a very clean modulation index of 2.5.
Let's apply this to the real world of standard FM broadcasting. Yeah, the exact kind you listen to in your car. Standard FM has a legally mandated maximum deviation of 75 kHz and a maximum modulating frequency for human hearing of 15 kHz. If you divide 75 by 15, we get a fixed deviation ratio of exactly 5. This standardized number is the magic rule that ensures every FM radio station fits neatly next to each other on the dial without overlapping.
Section 5. Comparing AM, FM, and PM. We have covered a lot of ground today, so let's tie the whole shebang together. Comparing these methods side by side reveals their fundamental differences. AM changes amplitude, FM changes frequency, PM changes phase. But I want you to look closely at the noise immunity row. FM delivers the absolute best noise immunity, which is exactly why we use it for TV and FM sound transmission. AM, on the other hand, has the least noise immunity, so it's mostly relegated to older TV picture transmission, where static just shows up as a little visual snow rather than unbearable audio noise. PM sits right in the middle, and it is heavily utilized today in modern digital and TV communications.
As we wrap up today's explainer, I want you to think about this. As bandwidth becomes even more precious in our fast-paced wireless world, which of these modulation methods do you think will dominate the future of digital communications? Understanding the past and present of AM, FM, and PM is really the only way to invent what comes next. If this lesson helps you clear up these concepts and get ready for your exams, please do me a huge favor. Like, share, comment, and subscribe to AJ Study B for more structured, clear, and focused learning. Keep studying hard, and I will see you in the next